So we have two start with both related to SPDEs. The first one is Hakon. Talk about multi-index Monte Carlo.
Thank you for the introduction, and I also would like to thank the organizers for a great workshop. So, let me. Oh, this. See what this is. Okay, let's see if this works. Right, so this is a joint work with Abdul, that was there earlier, and with Andreas Pettersson from Sweden. So in a nutshell, what we're going to look at is this kind of Hilbert space valued SPDE, which is given on top here, over some time interval, so from 0 to capital T. And we want to construct a numerical method for approximating quantities of interest of this SPDE, or Hilbert space valued SPDE, if you want. So our quantity of interest is denoted with the psi here, and it's a mapping from one space to another, so both separable Hilbert spaces. So it's a weak approximation method, and this is a very short form presentation of how it looks, this Monte Carlo method. So it's a multi-index Monte Carlo method. Unlike Giles' original method for SPDEs, it has two discretization parameters. So one is in time and one is in space. So we have two refinement indices. So one is n here and another is m. And then IL here just denotes the Monte Carlo sample, the IL Monte Carlo sample on multi-index level L. So it's a boldface L. And then you need to have this kind of coupling of realizations on the different levels in order to achieve variance reduction. And yeah, it's an extension of multilevel Monte Carlo that I will come back to the details of later. So we want to approximate the quantity of interest, which is something that is U valued, the expectation of the quantity of interest with our multi-index Monte Carlo method, and we want to achieve some kind of accuracy, epsilon squared in mean square error, at as low a cost as possible. You know, this kind of optimal Monte Carlo cost is epsilon to the -2, so we want to try to be close to that cost. And when you have two discretization parameters, you could imagine, or perhaps you know just from solving the heat equation numerically, that it's actually quite costly to solve partial differential equations numerically. And now you need to generate many samples of solutions of that type. So you would expect that perhaps the Monte Carlo method does not perform so well in this setting as it does for SPDEs, because it's just a problem with more degrees of freedom when you solve it numerically. Right, so maybe I should say something about how I plan to do this. So first, I will talk a bit about this Hilbert space valued ST, or stochastic partial differential equation, and the kind of solution notion that we want to look at. So we will look at mild solutions of an SPDE. Then I will give you some details on different Monte Carlo methods for approximating for doing the weak approximation. And I will present some general theory for multi-index Monte Carlo methods also for solving this problem. And then I will zoom in on one particular method which actually works for this purpose. It works pretty well. And it's not that easy to find a method that works for this purpose, actually. And then in the end, I will show you some numerical results. Okay, so a canonical example of the kind of equations we look at is a stochastic heat equation that is given on top here. So you should now think of capital X as a function both in time and space. So it's both in t and x. So x X here is belongs to some sort of domain D, which is a subspace of well, a D-dimensional domain, subspace of RD, and it's convex, or at least it has C2 boundary. I assume the initial has 0 boundary conditions, and I assume that the initial condition is given. So it's a reaction diffusion equation. If you look here, this is sort of a reaction term, and this can be nonlinear. And on top of that, we have this kind of additive noise. So this is a Q-winner process. It can be multiplicative as well. Right. So a way to view this minus Laplace operator that is on top there is that it is a mapping from this Sobolev space here, which is dense in the space L2, which is our Hilbert space. And it's a positive definite linear operator, which we can spectrally decompose. And that's important for the sort of approach that we are going to apply, because we're going to use a spectral Galerkin numerical method. So in this case, you can spectrally decompose the operator, and you know actually something about the eigenvalues also for this setting that I presented is, you know that the eigenvalues of the operator grows with this rate, depending on the physical dimension, according to Wales' law. So one classical example would be that you just take the one-dimensional domain, the interval between 0 and 1, and then you probably have seen in some PD course a long time ago that you can solve this using Fourier series. You can spectrally decompose the operator, and or in this case the sine series, and it takes the spectral decomposition takes this particular form because of the boundary conditions in this case, and here is the eigenvalues. The reaction term that we're going to look at is this kind of composition mappings. So this is something acting on a function, a Hilbert space valued thing, but the little f is just a scalar valued function. So this is often referred to as a MIMC operator. And we need some regularity, but I will come back to it. So the more abstract framework is the one which is presented here, and now we have replaced our Laplace operator with something more general. And we're working on a Hilbert space with this kind of inner product notation. But we're keeping the constraint that A here is a densely defined positive definite linear operator that we can spectrally decompose, and for which we actually know the eigenvalues. So we know also the rate of growth. So this is the parameter nu here, which relates to the regularity of the solution in some sense. And from this positive definite operator, we can generate sort of a whole family of positive definite operators by taking the power r of the operator and just associating it to the eigenvalues in the decomposition. And associated to these fractional positive operators, we also obtain a whole sequence of Hilbert spaces, which you could think of the energy norm of the square root of the AR operator. And yeah, so these Hilbert spaces are denoted .r, .hr. So .h0 is the original Hilbert space, and then you have, if R is positive, then this Hilbert space is going to be a subspace of your original Hilbert space, and if R is negative, then it's going to be a superspace of that Hilbert space. And the superspace is then constructed through the closure of the original space in the weaker norm. So the noise, the driving noise in the SPDEs that we look at, they are the form called Q-winner processes. And it's really a direct extension of kind of multidimensional normal distributions, so a vector in RD, say, but here your covariance operator, instead of being a matrix, is an operator on the Hilbert space H. You can associate it to your normal random variables. So if I take the inner product of my driving noise with some functions in the Hilbert space, phi and psi, then this is the expectation of two scalar valued random variables. And well, you have this relation. This is equal to the expression that I have here. So it's sort of a quadratic form of the operator multiplied with t. So the constraints we have on the operator Q is that it's non-negative, it's trace class. So the eigenvalues of this operator, the sum of them don't explode, they are summable. And it's alpha joint, and we can spectra decompose them. And for the framework that we're going to use, we actually assume that the spectral decomposition has the same eigenfunctions as the operator A itself. So we need some commutation in our proofs between these operators, and that's why this is convenient. And here is then the representation of the cube in a process. So you see it's a linear combination of standard Brownian motions in one dimension, these things, which are scaled according to the eigenvalues, and then multiplied with the eigenvectors, which are functions in space. And they are defined on this complete probability space, filtered probability space that is set there. I'm not going to say so much about the noise operator, but a little bit later on it. Right, so just to illustrate how the cube in a process looks for different kinds of covariance operators. If your mu j's decay with the rate, or mu j is equal to j to the -2, this is a trace class operator because you know that this sequence is summable, but you see that it's a fairly noisy random process if you want. Whereas if the decay rate is faster, then it's more regular. So this is just what this figure tries to illustrate. Right, so what about well-posedness of the SPDE? So let me first state the result. So if your initial condition is F0 measurable, so measurable with respect to the initial filtration, and it lies in this LP space, I believe you need it to be P equals at least 4, but not exactly sure. Then there exists a unique mild solution, which lies in this function space to the SPDE that we consider. And now the boundary condition is gone because now we sort of baked into the spectral decomposition of the operator, if you like. This is how the problem looks now. And okay, so what is a mild solution? This is the notion that we use. Well, it's an h-valued predictable process satisfying this kind of integral representation for the solution for each time. And you can think of this operator here as a semi-group operator. And so if you want, this is an extension of Duhamel's principle. So if I didn't have the noise term here, this would be, and if you had just this kind of evolution equation, this would be the way that you represented the solution in that case. But now I also have to add the diffusion term, the Ito integral. Right. So when it comes to numerical approximations of the quantity of interest of this SPDE, I have to introduce some notation for the numerical solution of the problem. So this is my notation for the numerical solution with some resolution parameters. So M here denotes somehow the number of time steps, and capital N denotes the number of eigenfunctions, for instance, or some discretization in space. So perhaps delta x is 1 over n. So this is just a generic notation for a generic numerical method approximating the SPDE. And then I'm going to have this notation for my quantity of interest. So it maps from the Hilbert space H into another separable Hilbert space U with this notation. Suppose now that I have some integer sequences of time resolution and space resolution in my numerical approximations, and they are both increasing, these integer sequences. And then I can say, well, suppose now M capital L and L capital L are very large numbers, and this is my weak approximation of the quantity of interest. Well, since the expectation is a linear operator, it satisfies this equality here. So I'm just exploiting that the right-hand side is a telescoping sum. And I can view this as an approximation, as a motivation of estimating the. I could say that, okay, I want to estimate the left side here by just taking a sample average of realizations of the left side. Or alternatively, I could estimate the left side by taking sample averages of each of the summands that I have on the right side here. And let me do that instead. So here I have like my approximation of the left side is through a sample average using ML samples on level L. And then I have this kind of linear combination. So the number of samples on different levels should be different in order to profit from this kind of approach. So this is essentially the idea by Giles from 2008 when he applied it to SPDEs. There were also earlier works by Heinrich in a different set. Stefan Heinrich. Right, so what is sort of the central point in this approach? Well, it's if you have a strong convergence, you actually need something that's really weaker. But if you have this kind of strong convergence here, so you have the rate beta 1, the mean square error rate beta 1 in time and beta 2 in space, for some positive betas, strictly positive. And if I choose my resolutions in time and space, so such that I sort of equilibrate the error contribution in time and space, the mean square error contributions, then this is an upper bound for the variance of the error from the L sample average estimator here, what I give here. So what you see is that the variance will be, at the very least, exponentially decreasing if I choose my resolutions the way I have described here. So if I go back to my representation here of the multi-level estimator, and if I want to ensure that the statistical error of my sample, my estimator here is small, I need to use very few samples on high levels because there the variance is low anyway. So this is really the core point there. But I may need to use very many samples, for instance, at level 0, but that's not so important because they are cheap to generate. So it's not going to make my method slow. Right. So if I now assume that my numerical method, so the cost of generating my numerical method and evaluating the quantity of interest of my numerical method is sort of multiplicative in time and space in this form. Typically, it would involve some log term of space as well. So you would typically have a log n here as well, but just for the sake of the slides, being more simple, I try to avoid log terms. Well, if I have this, then given the assumptions on the two previous slides, I can actually find sample numbers on the different levels such that my approximation is going to reach the kind of goal, mean square error epsilon squared, that I sought at the cost which is given here. So here I state the cost if I have some weak error rates, alpha, then the cost can actually become a bit less than if I bound the weak convergence rate by beta divided by 2. So you can bound it by that because you can associate the strong convergence by, you can associate the weak convergence to the strong convergence divided by 2. Right. So what I have here is an upper bound for the cost, but in many practical applications, this is what you use anyway, because it's very hard to estimate the weak convergence rate for many stochastic PDEs. So if I want to compare this to plain Monte Carlo, so plain Monte Carlo would simply be that I used a Monte Carlo method on the left side here. I generated as many samples that I needed to control the statistical error. If I were to do that under the same kind of convergence rate properties, my cost would be what is given down here. And what you see is that you have an improvement in the cost because there's a -1 in the exponent here that you don't have down here. I should say you have an improvement. You always have an improvement. Yeah, and this is related to a paper that we looked into this in some detail in a quite recent paper from 2022 that I wrote with Neil Chada and AJ Jastra and Georgios Sourais. But it has also been looked on before by Annika Lang, and yeah, many other people have looked at multilevel Monte Carlo methods for SPDEs. Right, so how do we extend multilevel Monte Carlo to multi-index Monte Carlo? So again, I have my left side here, where I have some fine resolutions, ML, NL. But now I replace my telescoping sum on the right side by a double telescoping sum. So now I have a telescoping sum in both parameters. And if I sort of impose that my summand here, when at least one of these parameters, L1 and L2, is equal to 0, then this actually becomes a double telescoping sum, and what I write here is true. And it's a sum of double differences that I have here, that I'm going to denote with this kind of delta L psi x. The double difference on level L1, L2 set is what I have there. And I take this representation as a motivation for my multi-index Monte Carlo method. So my multi-index Monte Carlo method is like a sum over two indices of sample averages of this delta L psi x. And my index set could, for instance, be a square box. This is what I have written here. This is just all the indices L1, L2 between capital L and 0. But it turns out it's typically not a smart idea to use a square box. If you study it in more detail, you see that typically it's smarter to use a triangular box where you actually decide the shape of the triangle based on the weak convergence rates of your method in both directions, and the computational cost of generating samples in refining the resolution in time or refining it in space. The setup. And here's a general kind of performance result for multi-index Monte Carlo methods for SPDEs. So suppose that you have a numerical method that converges weakly to the expectation of the quantity of interest, or yeah, converges in the sense that I'm given here, as the resolution parameters goes to infinity. And suppose on top of that, that for these double differences, we have a mean square error multiplicative convergence rate. So it converges sort of multiplicatively in the time and space directions. So it should be like delta t to some power multiplied with delta x to some power, if you prefer that kind of notation, for some parameters beta 1 and beta 2. Then the theorem says that there exists some weak convergence rates which have lower bounds, beta divided by 2, such that my multi-index Monte Carlo method is going to reach this kind of tolerance goal that we set at the computational cost, which is given, that is given here. It's epsilon to the -2, and then you have another exponent here, which depends on how fast your convergence rates are. So both sort of the strong and the weak convergence rates, if you want. But as I said, typically it's very hard to estimate what happened now. Let's see here. Typically it's very hard to estimate the weak convergence rates. So an upper bound for 2 times u is what I've given here. Then I just replace my alpha 1 and alpha 2 by the bounds that I stated here. Then you get this kind of complexity. So what you in particular see is if beta 1 and beta 2 are larger or equal to 1, then actually you're in the optimal regime. I mean, modulo this kind of log terms, because then the maximum of this expression is actually equal to 0. Another complication, which maybe shouldn't be in this result, but which we'll come back to for the exponential integrator, is that we actually do not see in all settings multiplicative convergence rates for the method. We see multiplicative rates plus some better mixed rates. And this is this was surprising to us, but this is reality. So, and then you have some factor theta, which is positive, and also some v, which is positive, which gives you a further improvement in the rate. And you also get sort of a corresponding improvement in the weak rate. And then this actually results in a reduction of u. So what we have down here now, don't know what happened, but yeah, what you have down there is a lower value for u in this set. And this actually also affects how your index looks. So with this kind of mixed rates on top of it, if you want to have the optimal index set, now it shouldn't be triangular anymore. It should sort of have a kink somewhere, depending on how these mixed rates look. Let me say a little bit about how multi-index Monte Carlo has been applied before to SPDE. So it has been applied to some linear SPDEs in filtering settings, for instance, by Cody and Cody Law and AJ Jasra. So then when your reaction term is linear, but when you look at well, here is another application. So in that case, it's not too hard to do the analysis, but it's challenging to do the computations anyway in the filtering setting. But it has also been studied for the Sakai equation. Also relates to filtering, but okay, it's another PD. So this is the SPD which is given on top here. It's different than the setting that we consider now for a few reasons. So the main reason is that the driving noise there is one-dimensional. So it's a scalar value b, and the equation that Reisinger and Wang considered had this kind of constant parameter beta rho here, which was between 0 and 1. And it had some initial condition, which was a Dirac delta. And they wanted to weakly approximate this in the sense that they wanted to integrate, I think, v from 0 to infinity at some point. Wanted to approximate that as well. So what did they do anyway? What kind of numerical methods did they look at? They first said, okay, can we use Milstein's scheme and mix it with finite difference in space? But if they try to use explicit integration in time, they hit upon this kind of stability condition, which is given here. So then your time step has to be very small compared to your spatial discretization. And that turns out to be no good for multi-index Monte Carlo, because in multi-index Monte Carlo, you have to allow for one parameter having very fine discretization and the other having very coarse discretization, and vice versa. But with this stability constraint, this, of course, does not apply. So well, general explicit schemes do seem to not perform so well, or at least unstable schemes do seem to perform not so well. So what they observed next was that if they instead used implicit integration in time, but still a Milstein scheme, then it's this scheme was stable, provided rho is sufficiently small. So if rho is smaller than 1 over square root of 2, they show that it was stable. Now, it turned out that for this particular equation, the multi-index Monte Carlo method actually didn't give any kind of performance gain over multi-level Monte Carlo. It's slightly surprising, but not so surprising when multi-level Monte Carlo already had the optimal complexity. So, but what was you could say is surprising is, of course, that multi-index Monte Carlo actually, at least in theoretically, is not able to sort of reproduce that kind of performance. So there's always some log term there in the analysis. I think in the numerical test, they saw similar performance also. Maybe there is room for improvement in the analysis. But what I'm trying to say here with this anyway is that this illustrates that it's quite difficult to find a suitable numerical scheme to use in your multi-index Monte Carlo method for SPDEs. And we started a bit similarly for our reaction diffusion SPDE. So we first tested implicit Euler for this, because this is a stable numerical method. But it has a problem in that it sort of smooths the noise a lot. So you don't get a very strong coupling between the different solutions in the noise, which actually exponential Euler does not have, at least when you have additive noise. But when you start having multiplicative noise, it's more unclear. So anyway, implicit Euler did not seem to work very well. So then we went to rather try exponential Euler. Exponential integrator, sorry. So this is the numerical scheme. So it's a spectral Galerkin method. So here I have some notation. M here is the time discretization parameter, and Pn is my orthogonal projection onto a subspace of my Hilbert space. So it's the n first basis functions. Then my numerical solution is this kind of Duhamel principle on the subspace. But then I also sort of freeze my coefficients here at every time grid. So this is the continuous representation of my numerical solution, which is defined on the grid, which is defined here. So that's the fixed values my solution takes. What's to say here? Yeah, so under the assumptions we have that when Q and A share eigenbases, you can often compute this second term here, which is f is typically nonlinear. You can often compute it using f of t. So you should think of it like this. We represent the capital N first modes, or the n first modes in this numerical approximation. This is our representation of the solution. We don't represent the solution in physical space over X. We represent it in modes, which I guess any Galerkin method would do. So, but the MIMC operator, which underlies this effort, it's a mapping on physical space, so or the solution U of X. So we then have to use the inverse Fourier transform to take this back to the values in physical space. Then we have to evaluate f of the inverse transform of the solution. Then we have to use the Fourier transform to take it back to the modes. Okay. So this is something you often can do, but it's actually very it's very hard to make it work right when you implement it on a computer. Okay, so some assumptions on our SPDE now. So we need to assume that our initial condition lies in this space here, so L10 and this Hilbert space, so it has this regularity. I need to assume some sort of coupling between the smoothing of my operator A and the noise in my Q in the process. And that coupling is done through this parameter kappa, which already was introduced there. So we assume that there exists some kappa. So this ensures that when I use Ito isometry on my the additive part of my Q in the process, it's something that's going to be bounded in terms of the spectrum. And here is now the linear operator. So sort of the multiplicative operator, G. It's of this form that is given here. So I suppose it's bilinear. And let me not say so much about it, but I think the main point is that, let me come back to the main point when I talk about generating noise. Okay. So the first paper that I'm aware of that considered the exponential integrator for solving this kind of reaction diffusion SPDEs was by Jensen and Klöden. And they showed that the method has a surprisingly nice property, namely that the convergence rate in time is essentially order 1, provided that your reaction operator is sufficiently smooth. So they impose this kind of twice shared differentiability conditions, which are given here. And I think a problem with this condition is that it's not so clear how wide it is. So it's not clear that it really applies to much more than a linear operator. Yeah. So we needed something, I mean, based on that comment, and also that our proofs are slightly different since we have to look at convergence rates for double differences, we rather impose that our operator is twice Cateau differentiable, and it maps down, so the second Cateau derivative has to map into some smoother space than H. Yeah. It needs to be Lipschitz, and well, it needs to satisfy the conditions that are given here in order for our double differences to have the appropriate convergence rates. But let me skip this now. Okay, so how is the computation of how do we solve this? I think we already have represented the numerical method, and this is just the values it takes at the different time points. But if I zoom in on mode K, and I just look on how the noise over one time step is generated that for the mode K, then it's going to look like what I have on the right-hand side here. And what you see about the particular form of our multiplicative operator here is that to leading order, the noise contribution is still associated to the K order Wiener process. I believe this is important in how we get the appropriate convergence rates of the double difference. If you now start to look at the next order, so sort of the iterated integral order, you will have some mixing in the noise, but to leading order you do not. Right. So under the regularity assumptions that was given, we can show that our numerical solution, and actually also the true solution, is going to be bounded or have this kind of spatial regularity for all times. It's going to be continuous, or it's going to have this kind of convergence rate in the space direction, which is given here, and in time direction, what is given here. And related to the double difference, so this is slightly more general than the double difference result, because here I'm just saying for any kind of differences between resolution parameters, I'm going to have the multiplicative convergence rates, which are still stated here. So kappa is somehow sort of the relation between the regularity of the Q Wiener process, or the Q Wiener process and the operator A. It tells you something about how much spatial regularity you get for your solution. And anyway, so these results that I have here, they result in the following kind of double difference convergence rates for the different settings of kappa for the given numerical method that we have. And I should also say, even although it isn't stated there, we have weak convergence for our exponential integrator method as well. So the result I gave before on the performance of multi-index Monte Carlo methods for a general numerical method for SPDEs that satisfy the assumptions applies to our exponential integrator method. Okay, so when you want to do the analysis and prove this, you have to look at the numerical solution representation of the double difference, and then you can split it into 4 terms. And let me just point out that a thing that is very nice with the exponential integrator is that, in particular, the additive noise term has 0 contribution, because that you can sample exactly. So the second order difference when you have the multiplicative noise is more challenging, but okay, we have restricted ourselves to so simple kind of multiplicative noise that we can control it using the regularity assumptions, twice Cateau differentiability, well, using the linearity of G in this case. Also, the initial condition doesn't have any influence. And the error related to the the double difference of the reaction term is something we can control based on the twice coupled differentiability. Skip this. And this is a summary of the kind of performance you achieve for different numerical methods. So the computational costs for approximating the SPDE we considered is given on top here, reaching the error mean square error epsilon minus square in the weak approximation, where the second exponent here has the following form for Monte Carlo, following form for multilevel Monte Carlo, and this form for multi-index Monte Carlo. And what you can see is that there is an improvement. There is an improvement every time you go to a new method here. So we have a rate improvement from multi-level to multi-index here. Okay. So let me just end with some numerical experiments. First, I just want to verify numerically that we actually see multiplicative convergence rates. So we solve some SPDE on different resolution levels, and we look at the double difference. So we take to study this, we take the Monte Carlo average of 10,000 samples, and we plot this for different L values, and we see that it should look like, if you take the log of this plot, it should look like a plane. But what I didn't say before is that we have actually a mixed rate in all settings. I didn't state on the results, but because we do not really profit from it in how we implement, but we don't see actually a plane. Let me try to, so the left-hand side here, so this is for the SPDE, which is given here. So this, now the reaction term is linear. Be an X, let's see. So anyway, here it's really so the intersection of two planes, which is exactly what you would expect if you have a mixed convergence rate as well. And here on the right, this is sort of a fitting to what you see on the left, and it aligns very well. A theory aligns very well with the numerical experiments. Our fitting give approximately the right rates. So these are the theoretical expected rates, and these are the fitted rates. You see. Here is a performance comparison of multi-level Monte Carlo and multi-index Monte Carlo. So on the left, they both we see that they both lie under some epsilon squared tolerance. So epsilon is in some sense an input parameter here, and I choose all my resolution parameters, MLs and my capital Ls and these things according to my input parameter epsilon. And you see that methods sort of perform with similar kind of mean square error. But then in terms of computational costs, the lower line here is essentially optimal, epsilon to the -2, and this is multi-index Monte Carlo. And the higher line is multi-level Monte Carlo, which is epsilon to the -3.5. And then here's a similar example, but this time with a nonlinear reaction term. And we see similar kind of results. Right, so then my time is up. I would just like to note that so Anna, which is talking next, has a paper where they actually sort of developed the convergence theory for more rough reaction terms. I think they used more advanced analysis than we did. But it would be interesting to see if we could also combine multi-index Monte Carlo with their approach. And I think this approach can also be applied to ensemble Kalman filtering, where we have done some work before with multilevel Monte Carlo. Okay, so with that, here is our archive preprint of the work, and thank you for listening.